Okay, let's put all the pieces together. We've got our function f, and we know that when we reflect its graph, we'll get the graph of f inverse. Complete inverse, partial inverse, still a reflection. And for notation purposes, I'll denote f inverse by g. Okay? Now, we know that if we've got a point x comma y on the graph of g, then it came via the reflection of the point y comma x on the graph of f. But the same thing would go for the tangent lines at those points. So here they are. And the slope of this tangent line is g prime of x. And the slope of this one is f prime of y, because it's at the point y comma x. This is what we were trying to get at in the previous problem. F prime of y and g prime of x are related because they're the slopes of these two lines, which are reflections of one another. The slope is the rise, the vertical distance, over the run, the horizontal distance. But up on the other line, those values get swapped. The horizontal distance here is equal to the vertical from before, whereas the vertical here is equal to the horizontal from before. And that tells us that the two slopes are reciprocals. For instance, this might be 5 and this 2, and that would tell us that the slope would be 5 halves down here. But then up above would have 2 and 5, and the slope of this line would then be 2/5. To summarize, we've got our g, which is equal to f inverse, and the derivative of g at x is equal to the reciprocal of the derivative of f at y. Or if you want to put everything in terms of x, we can replace y with g of x, and we'll get 1 over f prime of g of x. This will work as long as f actually does have a tangent line here to reflect. In other words, f prime of g of x has to exist, and it can't be 0. If f prime of g of x was equal to 0, then this tangent line would be horizontal, so its reflection would be vertical, and vertical lines don't have slope. That's what the formula would be trying to tell us. We'd be getting 1 over 0. So that's the geometric approach to the derivative of an inverse function. We can give an argument using formulas as well. We can start with this equation, f of g of x equals x for all x. And we know that that's true by the definition of inverse functions. So we can differentiate both sides with respect to x. On the right, we're getting d dx of x, which is just 1. And on the left, well, that's a composition, so we can use the chain rule. Now, we're presuming that f and g are differentiable here. But assuming that, we get the derivative of the outer function applied to the inner, and that's f prime of g of x, times the derivative of the inner function, g prime of x. And then, if you solve for g prime of x, you get 1 over f prime of g of x. Exactly what we got before. Hooray! This was a bit shorter than the geometric argument, but the geometric picture has a lot of really good intuition, and we hope you're able to get comfortable with both arguments. In any case, we now have our formula for the derivative of an inverse function. And it works whether g is a complete inverse of a 1-to-1 function or just a partial inverse. We have a few questions for you, and then when you come back, we'll cap everything off and calculate the derivatives of the inverse trig functions.